All right, so hello and welcome. Boy, so we're gonna try a LeetCode hard today. Figured I'd give that a shot. Also, yeah, I'm just, as I said, life's hard, man. I'm so sad. There's so many things they're just upsetting and difficult. Um, but anyway, I wanted to try this problem while we have some time here. Yeah, I have multiple problems that are just really difficult. That's where I'm at. Those of you wondering, like, what is he talking about? I just have like a whole boatload of difficult problems. That's really the issue. Um, but that's okay. We could just take it one step at a time. All right. So yeah. So we're gonna try a hard problem today. We're gonna try a hard one. Give it a shot. See how it goes. A median of two sorted arrays. Whew. Yeah, I gotta just like trust God. Slowly but surely, trust God. Slowly but surely, slowly but surely I'll have solutions to each of these problems that I'm facing. But yeah, way too many problems. So I thought about this problem last night. I have to kind of admit that I sort of already looked at this problem. I just noticed the name of it, and I was like, hey, maybe I could try some LeetCode hards and see how they go. And I realized actually this is yeah, it should be logarithmic. Yeah, I have an idea how to solve this. I thought about it and I was like, oh, I have an idea. I have an idea. So we're gonna write a subroutine. But basically the name of the problem kind of gives it away. Like you really don't have to read it. You can kind of know immediately what they're looking for. Given two sorted arrays, nums1 and nums2 of size m and n, respectively, return the median of the two sorted arrays. The overall runtime complexity should be O of log n, m plus n. Now notice, one sorted array, the median would be constant time. It's just immediately. It's the middle two. It's either the middle element if it's odd, or the average of the two middle elements if it's even. So here is a good example. Or actually, here it's just 2, because the merged array would be odd. But here, if it's even, you would do 2 and 3. And then 0, 0, 0, empty would give you 1. Oh, that's interesting. Oh, there's just one element. It's 1, and then one element is 2. So this is actually the solution. This is pretty straightforward, and I'll explain. But it's a little tricky to get it right. So we're 3 minutes in. It's a little tricky to get it right, but it's actually very straightforward. So what you do is you take you're going to perform like a sequence of logarithmic searches, and what you're going to do is say, okay, a sequence of binary searches, and the sequence of binary searches, well, we can make that like a subroutine, and then the other part of this is to call that subroutine potentially multiple times, depending on what the scenario is. So if you have an odd number, if m plus n is odd, then you would only need to call that routine once, starting from, we'll call them nums1 and nums2, we'll call them A and B. You can actually just rewrite this to just A and B. I prefer that. It's a little bit faster to code it without so many characters. You'd have A and B, so you can call that routine with A first and then B second, and then you can call it also with B to A. So the idea is you're gonna do a binary search through the first array, we'll call it A, and you're going to say, okay, start from the middle element, and find where is that element in the second array. And you could do a binary search to find where that element would be in the second array. And what that means is you would have n over 2 if it's n and m, right? You'd n over 2, or m and n. So m over 2 elements in the first array, and then whatever number you get, some call it alpha, in the second array. That means you have m over 2 plus alpha elements. That's the m over 2 plus alpha. That number, we'll call that j. This is the jth order statistic of your combined array, right? That's what that would mean. And what you want to do is you want to make sure, well, hey, if j is, if it's too small, right? In other words, we're looking for the median, which would be m plus n over 2 is the sort of, that's like, if we make that k, that's the kth order statistic. if j is less than k, the jth order statistic is smaller than the kth order statistic, then that means we need to increase the size of our value. So now we're going to look still in A, but we're going to look on the right side of A. We're going to split. Now we're going to update our binary search to the right side. The on the other side of things, the I gotta think about this too. Actually, I'm not sure about this time complexity. I could be wrong. I'm pretty sure it's logarithmic, but yeah. So now you do log of like so you can perform each of these routines, right? If maybe your order statistic now is too far, now it's above k, then you would need to go to the left side. So you keep kind of narrowing down the space for M or for A, right? You narrow it down. Now the problem is that you could never reach. So let's say we're in the odd case, right? You might have a situation where actually the median element is not in the A vector, or is not in the A list, the A array, the first array A. If it's not there, then you have some sort of a problem where you would need to do the same routine but backwards. Now you'd start from B and search in A. Until you get the correct, the kth order statistic. And then if you find it, then you're done. That's it. Actually, just return that. So it's that simple. And you would say one detail here is if it's odd, m plus n over 2, m plus n is the odd amount divided by 2. Yeah, I think that's correct. Yeah, you just divide by 2, should be fine. That should be the right index. So what happens next is, so you could do, so it's a logarithmic search. Now the thing is, the number of times you perform the logarithmic search you do, it's for a given m, you would do log of n. That's how long it takes to perform your search each time. I want to say it's not quite. This is actually a faster runtime than the one that I'm going for, the one that I have immediately. But then by the way, you could do the same thing for. That might be why I got so many downvotes. I don't know. Oh no, I got a lot of upvotes. Excuse me. It's got a lot of upvotes. Yeah, it's good. I'll give it an upvote too. I'll go with the crowd. Sorry. Did get a lot of downvotes, but I think it's way more upvotes than downvotes. I didn't realize there's an extra digit there. I thought that was one less digit. I didn't realize it's almost 13,000, not 1,200 or 1,300. So that's a good question. The next part though is that if you have an even total number, then you're actually going to perform these routines twice. So you're looking for 2 order statistics. And to find those 2 different order statistics, you're going to search in the first. You do AB to find the first order statistic, then you search BA to find the first order statistic. If you and then you go to the second. So that you would find the first one, and then to find the second one, you do the same thing. You do AB and then BA. So you do four times you do it if you're even, twice you do it if you're odd. So it's a little bit of extra kind of code to do that, but the basic idea is they're still the same. So now the problem with this is that this doesn't give you necessarily logarithmic log of m plus n time. This would give you, it's logarithmic in terms of n, and each time you call log of n, you get each time you call log of n, you get log of you would do log of m time to find where is this median value found, and that's kind of tricky because that's log of m times log of n, not log of m plus n. So there's it's left over from previously. That's log of m times log of n, because you would do once to cut in half, and then another time to cut in half again, and so on. How many times you would execute, and that's log of n times. And then each time you multiply that by O of log m. This is log m. This is to perform your binary search to find out what the order statistic is for the value that you're looking for in the other array. So also tricky here is you could have duplicates in theory, which I didn't really think about. So if you, let's just say return -1 or return 0, let's just double check if we could have duplicates or not. And that's also very challenging because of how our binary search is going to work. Okay, so that is a valid test case, 2 and 2. So yeah, so we could have duplicates in these arrays as well, which is very challenging because, and the reason why that's so challenging is that you kind of need to double check also, like a couple things here. One, we still don't have O of log m plus n, but we also have don't have O of m plus n, but we also don't have well, actually, that's maybe the first thing, right? We want to get, instead of log of m times log of n is not the same thing as log of m plus n. It's actually the log laws are log of mn is equal to log of m plus log of n, and log of m plus n is, I'm not quite sure, log of m times log of n is actually kind of interesting. It's actually log of n raised to log of m, which is kind of unusual. Kind of an interesting thing there. Which this is obviously n raised to log of m is not the same thing as m plus n, right? N plus m. In fact, if you change the base, you do log of m is I think you do log of m over log of n. Does that work? No. I think it was log of n 10. I think that's what, if you want to change this base, and then n raised to this log of n m over log 10. I don't know if it's log n of 10. I think it's something like this. I don't remember exactly the change of base, how it works. I tend to forget it. I think if you wanted, it's like log 10 over log 2 is equal to log base 2 of 10. Is that right? 1 divided by, which is log 10, divided by log 2 gives us log base 2 of 10. I think so, right? If you raise this to the power of 2, you should get 10. Yeah. That's all well and good, but so log of, if this is 10 m, this 2 would go down here, so you do log of does that work? You do. I think it's like this. I think it's, if you want this base, well, it happens to be base 10 here. You would take the log of the bottom part, which is log 10, and you put that with whatever base you want, and then the other part is the same as up there with another base. So this could be any arbitrary base. Log 10 over log 2 it could be any base x. Bottom part goes to the bottom, top part goes to the top. Subscript goes below and the other one doesn't. So yeah, so what's interesting about that is you do n raised to log n m over log n 10. That's equal to n log n m times, which could be times log n 10, which then gives you n raised to log n m. I think the way you multiply these are you can actually raise them to the same power, and that gives you multiplication. So then gives you m raised to 1 over log n10, which is the root power of log n10. Whatever that is, of m. What is going on? What is this? What is going on here? I don't know about this. I don't know about this. But clearly not n plus m. I don't think so. I don't think so. I don't think these are equal to each other. That's what I'm wondering. I don't think so. I don't think so. Now how? So, Now maybe there's a way to do this that is like a binary search on both that doesn't break them into two different binary searches. Maybe that's what we're doing wrong. Maybe that's what makes this hard. I was kind of wondering, like, I didn't think this is that hard, but maybe that's what makes this hard, is this condition. I don't think these are true. I don't think this is true. I don't think so. I would say it's not. All right, so maybe we have, let's take like a test example, like, I don't know, 1, 2, 2, 3, 4, 5. You also have to be careful about duplicates. That also makes things a little more complicated as well. And, you know, I don't know, 1, 3, 4, 5, 6, right? Something like this. 1, 2, 3, 4, 5, 6, plus, so we have 11. So we could do something like, I don't know. Lost my butt, man. My butt. It's killing me. We could take this middle element here, one of these, right? And then we can say, so it's 1, 2, 2, 3, 4, 5. That gives us 3 out of 11. So out of 11, we're looking for the so if you sort of ordered this 1 to 11, somewhere here you have 5, 6. So 6 to 11, how many numbers? 5 to 1 is 5, and 6 to 11 is 6, right? So 6 would be the one we want. So we're trying to get 6 out of 11. That's That's the number we want. So I guess we could start with 3 here, and then 1, 2, 3 here, right? Now, the tricky thing is we need to know how many numbers there are before either of these. That's what we want to know. So this clearly says 1, 2, 3, 3 numbers from here, and then we also want to get another 3 numbers from over here. Now the tricky part about that is every number. Maybe another way of doing this is that every number in this array has some position that we don't know. So if we were to 1, 2, 2, 1, 1, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, right? And really these sort of constitute a range where both of these numbers kind of have both of these positions. So that's kind of the deal with duplicates. Things get a little bit complicated there, but we don't need to get into that just yet. We can come back to that in a moment. But so this is the 0 and 1 statistic. This is 2 and 3, 4 and 5, 6 and 7, 8 and 9, and the 10th statistic. And we're looking for the middle, which is just 11 over 2 statistic, which gives you 5. Or I can take the floor. So this is the one we want. So you have 1, 2, 3, 4, 5 to the left, and 1, 2, 3, 4, 5 to the right. So that's what we're looking for. That's the target order statistic that we want. But each of these have, 0 and 1, 0 and 1. 2 is 2 and 3. They kind of share these statistics. 3 is 3 and 4, or yeah, 4 and 5. And then 4, you can kind of randomly assign these values different, whichever one's in the range, that works too. 6 and 7, 6 and 7, and then 5 gives you 8 and 9, 8 and 9. All right, and then finally 6 is 10. These are their positions. If you were to merge these two arrays, like every instance you have this problem, if you were to merge these arrays, every number would have a position in the merged array. And we're trying to find the median of this merged array in O of log of m plus n. So the total number of elements, we're going to do this in logarithmic time to find that value. Okay. So maybe we can split both pieces at each iteration. We can split m into 2 pieces and n into 2 pieces simultaneously while we try to find the median, and that would give us O of log m plus n. How we do it on time. So I don't actually have the solution to this. I have to think about this for a while. But that might be better. Instead of trying to basically search through these elements, and then each time there search through these elements as well to find out what its actual position is for each of these values. Again, there's also that issue of if you have multiple duplicates, then they could have multiple different potential values as well. Yeah, and gets a little confusing. I think it can get a little confusing. But yeah, so but I'm sure we can handle that. But let's not get into that yet. Let's just say we can assume for now that every number has a unique value. Like if all the numbers, if we could just presume for now we don't have any duplicates for the time being. I think the same algorithm, similar algorithm will work for duplicates as well. Kind of want to lay down and think about this. So, oops, didn't mean to do that. Actually moved, but hardly moved. Yeah, I think we're okay. Excuse me. Sometimes it's easier to use like tens instead of, so you do 10, 20, 30, 40, 50. And then it's easier to fit numbers in between. So you go like 15, 25, 35, 45, something like this. Or you can do like, 27, 28, 38. So you can do something like that. Now we don't want to do this in O of m plus n time, because you could merge these arrays and then do a binary search on the merged array, and that would work. Actually, you don't even have to do a binary search after that. Once you've merged it, you actually already have what you need. Maybe what you want to do is figure out, like, from left to right, how many values you would jump to get to the order statistic. I wonder if there's a way we could do this with a heap as well. I was wondering if you just like dump it into a heap, what would happen? No, the heap would give you linear of n plus m over 2. That's not what you want either. No, I think you want to use, a special kind of binary search. But that's a very custom, very special binary search, I think. So how might it work? I guess you could start with the midpoint of both arrays, right? 2 midpoints, and you would say, okay, that number you're looking at gives you some, well, the problem is that actually I guess you can start with 2 different numbers, but how can you very quickly determine how far into the array you are? Because it's not, I don't know why, it's not 2, I guess it'd be 2 pointers into the arrays or 2 indices into the arrays you want to manipulate in order to get this logarithmic behavior, but you also want to know, like, for each of these numbers, what the order statistic is. So I guess if you went to the midpoint of the top array and you picked one of these numbers, and then you said, let me look at the bottom number, the midpoint of the bottom there, and let me take a look at these 2 numbers. If I suppose you don't necessarily know what the order is of either of these, right? They could actually both be relatively small, I guess. Clearly the number of numbers to the left of both of these combined is half, and the number of numbers to the right combined is half. And I guess the question is, can you figure out, of those 4 possible ways to divide the numbers into half of the numbers, can we figure out which one of those should have the median order statistic that we're looking for, the 2 different statistics that we're looking for, right? We could kind of do both. The particular order statistic that we're looking for, can we find that? Now, what's interesting here also is that it's kind of special that it's the median that we're looking for, because I think if it was just an arbitrary order statistic, then you wouldn't be able to find it in logarithmic time, because I think even well, no, if you have a sorted array, an order statistic is constant time, so I take it back. That's not true. It probably could work for any order statistic, which in the even case, we're searching for 2. Excuse me, so presumably we're gonna run this iteration twice in the even cases to find a particular order statistic. So, all right, so we go to the middle and we say, all right, can we answer that question of how many elements are to the left, how many elements to the right? Oh, what is going on? Hold on a second. Got some YouTube videos going here. Hopefully it's muted. I think it is. Yeah, good. Very good. Just starts running ads. I think it was muted. All right. So the question is, yeah, we want to do something a little bit more special than just like a simple, like double search, double binary search. We want to know, like, obviously we have we can get the median of both of the arrays immediately, but we're looking for the median of the combined array. We don't necessarily know how they're combined. So the median of the combined array could take some number of elements from the left side of the first median and some number of elements of the left side of the second median. And I guess what I mean is the median of the combined array could take some number of elements from the left side and the right side of the medians from both of these arrays. Those could be some number of elements from either array will be on the left side. Now, yeah, because they're interleaved, right? These numbers are interleaved. Right, and then same thing with the numbers that are left over. They're interleaved on the right side of the median of the combined array. So, trying to think, maybe there's a way we can figure out how many elements are interleaved. Yeah, how many interleaved elements? Like, clearly, there's something special about taking the medians of both of the arrays, because the number of interleaved elements, if we add it on both the left sides and the right sides, like that's the number of interleaved numbers for the median that we're looking for. So I guess what we can say is, like, we've split into 4 pieces our arrays, and in one of those arrays is the median, or it's one of the 2 elements we're looking at already. Something like that. I mean, what I'm trying to do is kind of split both arrays into 2 pieces repeatedly. That's kind of what I want to look to do. And that should give us log of n plus n time. Yeah, something like that. Yes, basically break down all the elements that we have, break it into 2 pieces repeatedly. So what we can do is we can break into 4 pieces and then just select 2 of those 4 pieces at each step, right? And if we did that, then we'd be fine. So we can somehow determine that some combination of those 4 pieces is what we want, like 2 of those 4 pieces is what we want. And then we could take the midpoint of those again and then repeat the same routine and do that over and over again. That would give us log of n plus n time. Question is, though, how do we do that? How do we know the median is going to be either to the left or possibly to the left or to the right of the... Like, how can we know with certainty it's not to the right or to the left of the first array? Let's start with that. Like, if we can eliminate one of those 2 pairs, and then on the second part, eliminate one of those 2 pairs as well. Well, I suppose I suppose let's say the median value that we picked in the top is larger than the median value we picked in the bottom, right? So these obviously they could be equal to each other, but suppose they're not equal to each other, right? So that means all the numbers to the left of the top one are smaller than the median, and all the numbers to the right are larger, and they're also all the numbers to the right are larger than the median in the second array as well. So what does that mean? That means that the number of numbers that are larger than the smaller element in the array, that is, let's say if we had 11 elements, that means that we would have 5 to the right, and also, well, let's say both of these arrays are for one, the top one is 5 and the bottom one is 6, right? So if we take the median of both, then the number of elements to the right, and let's take the lower median of the second one. There's 3 elements to the right, and there's 2 elements to the right on the top one. The 2 elements on the top one that are larger, if the top one is also the top median is larger than the bottom median, we can eliminate those 2 elements as possibly being the medians because there's going to be 3 elements that are smaller in the top one, and also because it's larger, the 3 elements in the bottom are also smaller. So there's 6 elements that are smaller, which means that is too far to the right. Right? It's got to be 5 elements that are smaller, not 6. So we can eliminate the top right portion immediately. And I think we do the same thing on the bottom elements as well. We could say for the ones that are smaller, so we said on the bottom side that this value is smaller than the top median. Those smaller values are there's too many of them. We would have 2, or actually no, that may not be correct. Well, we don't have to get rid of all of them, but we can get rid of, I would say, oh, that's actually kind of tricky. Well, we can definitely eliminate those larger values I was talking about. That's certainly true. But can we eliminate the? Huh? Can we do that? Because the problem, I guess, is that for some of these we know that too many to the right are larger. But also we could say too many to the left are smaller too. I think that's kind of what I want to say. I want to somehow do something with these equality operators so that way we can figure out, like, hey, there's too many things to the left are smaller, too many things to the right are larger. I would say, actually, it's probably better to say too many things are smaller. That's probably the better way to say it. So for the things in array A to the right of the median that are larger than the median of A, and they're also, all of those are, since the median of A is larger than the median of B, those are all larger than, we said there would be, there's 3 elements in B and 3 elements in A. So all of those have 6 elements that are smaller or more, which means they're too far. So all of those larger values are too big. The smaller values, the ones that are to the left of the median array A and median array B. So I guess the ones that are the smallest values would be the ones that are to the left of median B. Those have 3 elements that are larger. They're all smaller than B, median B, right? So they have 4 elements that are larger, and then also they have all of the larger elements from array A, median A, since these are also small. They're smaller than median A, everything to the right of median A, which including median A, which is 3 elements. There's 4 elements to the right plus those 3 elements to the right. There's 7 elements to the right, so those are all too small. In fact, I would say even median B is too small because it would have 3 elements to the right and it's smaller than the top array, so it also has 3 elements to the right and also another 3 elements to the right, which puts 6 elements to the right. So we can eliminate the 3 on the left in median B and the 2 on the right in median A. And then now you're left with a range of A. So now you can modify your range for A and B and what array A and what array B might the elements that are left over to consider. So yeah, I guess you could do it that way. I think eliminate each. You break the array into 2 pieces based off of the midpoint, 2 midpoints, and then you can eliminate based off of how many, whatever order statistic you're looking for. Obviously, if you have an even total number of elements, you're looking for 2 different order statistics. You could do it. You could run this routine twice. First the first order statistic, second the second order statistic. But if it's odd, obviously it's just 1 order statistic you're looking for, so you just run it once. In the even case, you would take the average of those 2. But for each iteration, what you would do is you break the array into 2 pieces, either roughly equal size, and then you would say you would eliminate a number of elements based off of how many elements need to be larger and how many elements need to be smaller for that particular order statistic, and knowing that at a certain point all of those elements it would have too many, and all of the other elements have too many, either too many smaller elements or too many larger elements. You can break down your array further and further, and I think it would be in each case you throw out half of the total elements, which gives you log of n plus m as desired. I think that works. I think you do it that way. That's a slightly better running time. That's definitely more challenging, though. That's definitely pretty clever. I guess that's why it's got so many upvotes. It's a pretty clever approach. And kind of tricky to code it too, because you have to guarantee you can throw something out each time. So yeah, so after you throw out the right half from the top array and the left half from the bottom array, then you find these 2 new medians again. And the thing is, you still I think counting is the way you want to do it. You still could compute constant time how many elements are to the left or to the right of whatever positions you're considering, and sort of which ones are smaller or greater. Yeah, it definitely gets kind of tricky, but I guess you would basically just figure out the smallest elements and the largest elements. You can kind of just keep throwing those out. I think that's kind of what it comes down to. Yeah. And then you kind of slowly narrow it down to I guess two different elements, and then one of those 2 elements has to be the order statistic that you're looking for. Yeah, because I guess at the end of it, you have keep throwing out elements until you realize that one of these pointers should disappear altogether, or you just don't have enough. You just have too many elements on one side or the other. How would you handle that at the end? Yeah, I guess. Well, we can walk through an example. That's probably a good idea. Walking through an example is a good idea. I think it's not bad. Oh, okay. And then once we do that, then we can look to program that. Oh, this is getting a blood rush. stood up in my, ooh, my body. Yeah, man, wow, okay. Thinking a lot lately about my blood and pressure and things like that because, not blood pressure, but just because pressure in general because my, having issues with going to the bathroom, bleeding. When you bleed, when you go to the bathroom, it's not fun. All right, so we can do with duplicates too. I think it works the same with duplicates. 1, 2, 2, 3, 4, 5, and 1, 3, 4, 5, 6. All right, so this is 1, 2, 3, 4, 5, 6, 11. The order statistic is 11 over 2. OS, we'll call it, order statistic, which is just fifth order statistic out of, really it would be the sixth. If the first order statistic is the first value, the smallest value, and the 11th is the largest. But it's really the fifth index. Index 5, rather. All right, so now what we would do is we would start at the middle, and we would say there are 2 to the left of 2. 2 smaller than 2. So 2 is less than 4, right? So that means there are 3, so 2 left of 4, excuse me, 2 larger than 4 plus, so these 2 that are larger than 4 are also larger than 3, larger than 2, right? Gives you 5. So it's actually, it's actually the other way around. So it's 5 and 6 are larger than 1, 3, 4, which the size is 3, plus the size of 1, 2, 2, which is 3, which gives you 6. Therefore, thus, 5 and 6 are eliminated. Are eliminated. A little fast to type it. Okay. And to draw it with a brush. So 5 and 6, we can eliminate 5 and 6 on the first round. Same thing, 1 and 2 also are eliminated. So, and actually 3 is eliminated too, I think. We could say 1, 2, 2 equals 3 plus no, excuse me, 3, 4, 5. It's the other way around. 3, 4, 5 equals 3 plus 4, 5, 6 equals 3. Gives you 6 elements elements are all larger than 2, and so 2 and anything less than 2 in the first array cannot be the median. Right, so we could eliminate medians in this way. Right, it's pretty clever. Pretty clever. If I do say so myself, pretty clever. For having less than 3 and less than 2 over here actually means 4 could still be a median, right? Because we need to have 5 things less than this value, right? So now we say I'll update to the next medians of what's left, right? The midpoints of what's left. That's constant time to do that. So it's constant time to eliminate these values. To do one iteration there, and then now we say, let's take green for the next one. So now we say 4 is greater than 3. The smaller values for 3, 1, has to the right of it 1, 2, 3, 4, and also 5, 6, right? So there's 2 here plus these 4. So we would say for each element smaller and possibly including the smaller median in the array containing the smaller median. There are too many elements that are larger than these elements. Then x cannot be desired median. Similarly, for each element y, larger and possibly including median in the array containing larger of the 2 medians. There are too many elements smaller than x than y. So we can eliminate these pieces. And that's sort of the algorithm that we're going to use to eliminate these pieces. It's kind of hard to explain it, though. It's kind of hard to see it. How are we doing? Almost an hour into this? Okay. Fair enough. So now we would eliminate, we would say 1 has, in fact 1 and 3 are good examples where, since these are smaller than 4, we have 5 elements that are larger than 3 and 6 elements that are larger than 1. So 1 is eliminated because that's 4 elements plus 2 elements gives you 6 elements that are larger than 1, which is too many. Right? We could say we need 6 to the left. The median would have 5 to the left and 5 to the right. And then so has 6. That's too many. And then on this side, 4, the things that are larger, right? So 4 is larger than 3. and so it's larger than 1 and 3, 1, 2, 3, 4. So that actually, oh, excuse me, 4 is larger than 1, 2, 3. Yeah, 1, 2, 3, 4, 5, 6. So 4 is larger than too many things, and then 5 is also larger than too many things. Similarly, right? So 1 is smaller than too many things, so we have 4 to the right, as well as these ones to the right. So that's 6 to the right, and then this 4 is and possibly including, right, including the smaller and the median. Yeah. So 4 has 4 things to the left, and it's also larger than the other median, so it has 6 things that's larger than. So that's no good. And then everything to the right of that is also larger than too many things, right? So eliminate both of those. And so we eliminate all of those, and so now we can say the next what's left over, 3, and here we would do 3 again, right? Which is fine. We could just do to take the left side. Let's do orange. We would say 3 has, can we eliminate this 3? So they're actually the same now, which makes things a little bit more interesting. We would say what's to the left of this 3 and what's to the right of this 3. So anything that's to the left of this 3 is also going to be to the left of this 3, and everything to the right of this 3 is also to the right of this 3. So this 3 to the right, we say there is 5 things that are larger, right? We have 1, 2, 3, 4, 5. And then to the left of this 3, we have 1, 2, 3. I guess to both. So I guess for both of them, really, if you have the same, if you have a duplicate, you can actually just say, like, I guess you could just count how many things to the left, how many things to the right. Like that's actually kind of tricky. I'm not sure exactly what happens with duplicates. I think it gets a little more complicated. Maybe we should just do it without duplicates. Without duplicates, I think this works reasonably well. But with duplicates, I'm not sure exactly. You have to modify it slightly, I think. But you would say there is actually 5 to the right of 3. So actually that once you have the right number to the right, I think you're done. I think that's all you need. Yeah, because you can guarantee that there's, if you can guarantee that there's 5 to the right or 5 to the left, well, guaranteeing, yeah, well, in this case, guaranteeing the right amount that are to the right is the equivalent to guaranteeing the right amount to the left. So if you can guarantee that there's 5, 1, 2, 3, 4, 5, that's actually it. When they're equal to each other, you would add the things to the left and things to the right. But the thing is, like, you could have, yeah, I guess that's fine. I guess I'm just thinking, like, what do you do if it's not? In this case, you could kind of terminate early because of that. But there may be cases where you can't, right? When they're equal to each other, then you have to somehow eliminate things. Just thinking. Yeah, I mean, you could still eliminate, like, so it's a little different when they're equal to each other. I think we have to consider that. So if they're equal to each other, then you can combine. So you can say everything to the left of this 3 plus everything to the left of this 3 gives you 4, which means there's not enough for this 3 to be the median. And then, well, but you can move these values wherever you want, though. So you could swap them if you need it. So you could say this is 3 to the left, but you could do plus or minus 1 then, I think. And you could say 3 plus 2 gives you that this 3 could be in the right spot, right? If we put this 3 in front. You could sort of move your 3s wherever you need them, I guess. And then, so that actually gives you 5, which means you're done. You have 5 on the left side, right? 3 plus 2 is 5, and then you could also do 3 plus 2 gives you 5 on the right. You do the same thing for this 3, which is 1 plus 4 is 5, and then 3 plus 2 is 5 as well. So yeah, when they're equal to each other, it gets a little funky. But yeah, if you have duplicates, you get enough of that position. Shouldn't really matter, I think, for the duplicates. I think it's only when they're equal to each other then your calculation changes a bit, because you can move your value into the right spot. Yeah. Then you'd actually just be done. Now, that's a little different though. Like, I want to eliminate things though, right? Like, when they're equal, it gets a little weird because you actually wouldn't eliminate either of these medians. Both of them could be maneuvered into the right spot. Yeah, but if we were not using duplicates, so we'll just say duplicate cases. Duplicate case where medians are equal to each other. More complicated. Medians themselves can be moved front, behind, can be maneuvered, have those positions swapped. Yeah, I think it's actually not such a big deal because you only need one element for your order statistic, so it's fine to eliminate. Like, if we look at this 3 and we say, okay, including this 3 and to the right, we can put these to the right of this 3 and then say there's 3 here and 3 here, and then this would get eliminated. You could do it that way. And then you would say this 4, we would say this 4 is larger than these 4 and these 2, so this 4 would get eliminated as well. So you could actually eliminate 4. So everything to the right of 3, we would say all of those, you would do plus 2 and then plus all 4 here, rather than, and then you could also say, like, you can do, you could do something like, I think at this point you could do something like, okay, because they're equal, let's try to eliminate something. Let's try to eliminate one of them, right? So we'd say itself and everything to the right, we'll say that is larger. Those 4 are larger than this 3. And so they're larger than these 4 and this 5. We would say, well, actually, that would give you 5. That's actually fine. But if we said everything to the right of this 3 is also greater than all the values in this 3, and these 2, that would eliminate these ones, right? Which we already did, but we'd eliminate them again. And then we would say this 3. I want to say that we could put, no, actually, yeah, it's kind of tricky. I guess you eliminate, yeah, you eliminate the 4. You don't necessarily eliminate this 3 because this 3 only has 3 larger, or excuse me, this 3 only has 5 that are smaller. At most 5, so we would eliminate 4 on the right. We wouldn't actually eliminate this 3. I think we could eliminate this 3 though. You could say this 3 is, it has too many things that are larger to the right. So you could say it's 1, 2 to the right, 3, 4, 5, but also the other 3. So you could say all 4 of these plus 2 gives you 6. So you eliminate those 2. I don't think you could actually eliminate. Trying to get, how would I use it? Too many things to the right, or too many things to the left. You could do 1, 2, 3, 4, 5, 6 to eliminate these guys, and then to eliminate this 3. That's the thing with the when they're equal to each other, like you don't know which sides to eliminate anymore, right? Because they're kind of, it's somewhat random, I guess. What numbers you have on the left and the right. Like, it's not that you can't. It's actually it's just more interesting. So you could say when the medians are equal to each other, may consider one larger than the other, and add 1. Two sections of 4 of the arrays, order to eliminate elements. Yeah, I think that's the way to do it. So you can actually, when they're equal to each other, you can declare one to be larger than the other, and do it that way. So we would and vice versa. So you could say, suppose 3 is larger, this 3 is larger than the second 3, then that means that we already eliminated these elements, but we'd say these 2, or all 3 of these are larger than these 3 elements on the left, and these 2 elements, they're all larger than 5. These would get eliminated again. You would say these 2 are larger than these 4 and these 2. So these would get eliminated again. And similarly, you can say then to eliminate the ones on the left, you'd say suppose this 3 is less than this 3. So now these 4 on the right are larger than all of these elements plus these 3. So all of these would get eliminated again. And actually, you would eliminate this 3 there because you'd say these 4 are larger plus these 2 that are larger, and so this would get eliminated. And same thing down here. You would say, suppose this 3 is, it could be smaller or larger as needed. So let's say it's large. So let's say if the elements on the left side we want to eliminate, these are large. This is smaller than all of these, and smaller than these. So that would give you 7. So that was get eliminated again. And then the ones on the right to consider, those are it's these 2 3s are smaller, and these 4 3s are smaller. So this 4 would be eliminated, and then this 3 would say it's larger than these 4 and this 1, which gives you actually 5, which is actually perfect. So you could eliminate one of the 3s and one of the 4s in that way. So you could do both. So you could do it that way. You could do both. A is less than B, and then B is less than A, to process it that way. So if you know what the relationship is, then it's clear. But then if they're equal to each other, then you can actually do both. You can do both when you're trying to figure out how many elements are to the left, how many elements are to the right, and you eliminate elements based on that. And you know how many you need to have on the left and how many you need to have on the right. So if there's too many elements that are larger, you can eliminate this element. If there are too many elements that are smaller, then you can eliminate, and you know how many you need to have that are smaller and how many they need to have larger, depending on that. And you can do that by the order statistic. It doesn't have to actually be the median as well. So that way, that allows us to do, for even cases, we can just run the routine twice, once for the sort of 12 divided by 2 order statistic, which would be the sixth, and then I guess it would be you subtract 1 to get you 5 and 6. So if you had 12 elements, if you even number, you have 0 to 11. Halfway would be probably 5 and 6, I think. So 0 to 5 is 6 elements. 6 to 11 is 11 minus 6 plus 1 is also 6 elements. Yeah, so you do 5 and 6. So this would be your 6th and 7th statistics, or it would be index 5 and index 6, which is 11 over 2 floor and 11 over 2 floor plus 1. Or excuse me, 12 over 2, and then 12 over 2 minus 1. Yeah, which is a little confusing, but it would be sort of the index divided by 2. So if you had 11 elements, the index is minus 1 divided by 2 gives you 5. The 5th index, which is the 6th element, and then 12 minus 1 over 2 will give you 5.5, which means you take the floor of that and the roof of that, or the ceiling of that, and that gives you your, you can do it that way too, you just subtract 1, and if it's odd, you'll get the right index. If it's even, you should take the floor, the ceiling, take the floor and the ceiling of n minus 1 over 2 to get you the two order statistics. And so you run the same routine you ran before, with just 2 different order statistics, 2 different values, different numbers. And you can eliminate the left, eliminate the right based off of how many elements you need to have. And again, you do more processing when they're equal to each other and the medians are equal, because you sort of would do both of these cases. You would say assume this one is larger than the other and go from there, and then vice versa, assume the other is larger and then eliminate elements that way. Yeah, interesting. So, and the way you eliminate these elements, by the way, is just keep shrinking the left and right bounds of the array. Just make them closer and closer until they're either on top of each other or they move. Once they're on top of each other and you eliminate that element, then you would just move them past each other, and then you wouldn't consider that array anymore. And you should end up at some point when one of these two numbers, one of them two medians themselves are equal to that order statistic that you're looking for. Have the right amount on the left and the right. Yeah, and then you return that, and then you're done. So kind of involved, kind of complicated, pretty interesting though. I see why it's a hard problem. This is a problem that, like, I haven't even coded it. It's already an hour into it. Let me just like sit for a moment, just ponder, think. I haven't even coded it, and I like it's like I'm just already done. It's like it's too much. It's a lot. Also, I think my mic is kind of high, the volume. I'm gonna lower the volume a little bit so I can talk louder. Yeah. So right. Oh boy. Oh, my sister texted me. Wow. Oh, wow. Dude, I'm losing my mind. Whoa. Dude, that's wild. Oh, man. My sister just gave me some news. It's just like kind of mind-boggling. Um, Whoa. Whoa. Brother, I don't even know what to think. That is just astounding. What? Sorry, I just got some news. It's just kind of like absolutely baffling. Wow. Dude, I don't deserve, like, there's a lot I just don't deserve in life. There's a lot I just don't deserve in life. That's crazy. Wow. I don't even know what to say. Brother, I don't want to say it what happened, but let's just say like something very unexpected happened, and it's just like I can't even like fathom, can't even process what's happening. Wow. Wow. Wow, 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 wow. Oh boy. No kidding. Okay. All right. Let me try to code this. Let me try to program this. And because I want to talk to my sister. Um, Brother, I'm undeserving to an extreme. Dude, that's, yeah, extremely undeserving. Extremely undeserving. I am not a good person. Don't deserve it. Oh man. Wow. Anyway, let's try to program this. Let's try to program this. Whoa. Whoa. Whoa, 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 whoa. Whoa. Okay. All right. So let's say we're gonna have a subroutine. We'll call it the find the ith order statistic, or yeah, auto order stat, and we're gonna say we're not gonna take it. We're gonna just have an int x. Really, int x is fine. I like to do that from time to time to make it const, so that means so we know we can't change it. But I actually think that's fine to do this. I think it's fine. I think it's better habit, better practice. That way, if you try to modify it, you know that you made a mistake. A and B. I'm quite undeserving. So okay. So we're gonna have our. So this is like the meat of the algorithm is gonna go here. So we're gonna say a while loop, and we're going to say whenever I think we'll return. We could return the number. We don't actually have to return the index. We could return the index though if we wanted to. All right. So I have a while loop. We'll just say while true. We want to. what was I saying? Oh, my body. Oh, my body, my body. A and B, X, well, true. O of log n plus n. What am I doing? Sorry, I'm just, it's kind of a hard problem. It's kind of a hard problem. Dude, I'm not a good person. I'm just not a good person. Not a good person. Sorry, I can't get over it. I am just not a good person. I don't know. I'm sorry. Sorry. Okay. All right. Each element X smaller and possibly including the smaller median in the array containing the small. Yeah. So there's three different cases, right? So we have the two medians. We'll say. Okay. So we'll say int mid 1 or just mid A is going to be. It's going to do left A. Starts off at 0. Left A, left and right A is A dot size minus 1. And mid A is going to be, oh, we'll do that next. Right, so you have left A, left B, right B. And then we're going to say int mid A is going to be left A plus right A divided by 2. And mid B is the same thing. Right A. And maybe I could make this a subroutine also. Maybe I should do that. Just midpoint. Just a small lambda function just so. I don't know, maybe that should be inlined. Maybe I shouldn't do this. Nah, it's fine. I mean, it's fine. It's fine. That's something you inline. It's perfectly fine to inline this. Left B plus right B over 2. Okay. So mid A, mid B, left A, left B, right B. How are we doing on time? Hour and 20 minutes. Okay. So what we're going to say is, so we have 4 cases. We could say, mid A, mid B. We could recalculate them. We probably should do that first. Could really just declare these here. Well, calculate them once, calculate them again. That's fine. And we'll say if. So we'll say int median A equals A of mid A, median of B equals B of mid B, and we're going to say if median A is less than median B, else if median A is greater than median B, and finally, otherwise they're equal to each other, right? There's 3 different possibilities, and we'll say so total smaller based off of X, the order statistic. We're going to say the target smaller or total smaller is going to be so we're going to say int total is A dot size plus b dot size. Total smaller is going to be the total minus x. Is that right? No. That's the total larger. Total minus x. So I think, and these are indices. So you would add 1 to the index. Yeah. So that's the total larger. The total smaller is actually x plus 1. And it's actually x plus 1 minus 1, which is kind of interesting. So if you have 11 elements and you want the fifth index, so 6 elements, the fifth index, you have 5 elements to the left, which is x plus 1 minus 1, and then the total larger is the total number of elements minus all the smaller ones and the element itself. So it would be minus x minus 1. Yeah. Which is kind of interesting. So x plus 1 would be all those elements. So the elements left over, that's the total larger, right? So this is for each order statistic. Now, if it's totally in the middle, then this doesn't really change. And this actually, both of these should be constants, right? They shouldn't change. Const references. Okay. These also don't change. This total doesn't change. These values, on the other hand, will change. But the total smaller, total larger, we can calculate those. Now, the tricky part here is we want to see if we can eliminate each piece. So we would say, excuse me, if median A is less than median of B, then the things that are to the left possibly eliminate, or definitely eliminate values to the left of med A, and you can actually you could do something like this. If med A equals med B, do something. Otherwise, const int reference. So we're actually going to take, like A or X, we'll say X and Y. We could have pointer, so we can do, we're going to do something kind of interesting. So const int A is going to be equal to the smaller of the two, and const int B, or Y, we'll do X and Y. X will be pointing to the smaller, and Y is pointing to the larger. And the idea is, actually, this is kind of tricky. I don't know if we can do it this way. What I want to do is, like when we eliminate, we update left A and right A appropriately, left B and right B appropriately. But we want these values to correspond. We can make like a struct. Actually, it might be better. Just have a struct here of just like a range. Left, range. Have left, right. Oh, it's time for me to eat. Uh-oh. All right, let me set another timer for like 30 minutes. Oh, we'll come back to this problem if I'm still working on it. It's kind of stuck on it. Set an alarm for 30 minutes. So we have left, right, and then I guess the midpoint. I'm trying to think, how do we want to do this? mid, left, right, mid. I mean, that should be fine. We'll just have like range A, and B. We'll say A dot left equals 0, A dot right equals A dot size minus 1, and not AB, range AB, where we could say, like, I don't know, alpha, beta, something like that. Could do it that way. I want to say something more like XY, actually. That's maybe better. And I'll kind of explain why we're doing it this way. So we have X, let's say alpha, beta. That's fine. Alpha, beta. That should be fine. Alpha, beta. And then beta left, beta right is b dot size minus 1. And then we can say mid A, mid B could be alpha left plus alpha dot right. I'll try to explain why I'm doing it this way. Beta dot left, beta dot right. Okay, and then we median A, median B. So the reason why we want to do this is we want to swap. We want an easy way to reference each array and the medians and the midpoints. Yeah, so the thing about this is, do we actually need to know? Basically, we want to associate all these values with each other. Like we want to associate left, right, mid, and median. All of those things, we want to associate all of those with a single range, and then all the other things with another range. That's why I'm trying to organize this somewhat. That way, if we have references to one, if we swap the references, then sort of everything swaps as well. But yeah, I guess we can come back to that in a moment. Like this is fine for now if we do this. And then now we can have a range reference to, we could basically have a range reference X and Y, and we could swap them so the alpha, X will be referring to the smaller range and Y is referring to the larger. And by small and larger, I mean their medians. The smaller median is the X and the larger median is Y. And then then our code could be a little more concise, right? Because then it's sort of every case is handled. Like there's multiple different cases, we can just kind of sort of organize them a little bit more so that we don't have to write duplicated code. That's the idea, but actually the implementation here is like a little bit challenging. Because the medians aren't going to swap with the associated ranges, right? What you can do is you can write the midpoint and the medians, so you can do mid and median, and you can say alpha mid. How about that? Alpha mid, and then beta mid. How we do it that way? And then alpha med, and then beta med. Of alpha mid and beta mid. Yeah, that should be fine. And so now we can update appropriately. I stopped updating my malware bytes because it's every time I update it, it gives me the premium, like a free trial, which I don't want or need, and I don't want to I just want the free version. I don't want the I don't want the I don't want what they're trying to sell me. Just don't want it. I just don't want it. So if alpha med is less than beta or greater than beta med, then we do the following. And what we want to do is actually we want pointers. So we're going to have we're going to say range pointer, const range pointer of T1 and T2, and we're going to point these to the address of alpha. So I've done this before, but this is a trick, a way of and T2 to beta. This is a way of setting up references, const references, when one thing is larger than the other. So if first we have T1 is to alpha, T2 is to beta, and if alpha happens to be larger than beta, then we would swap the two. So we standard swap the pointers T1 and T2, and then now we can set up our range references, X and Y. So now X is going to be whatever T1 is pointing to, and Y is whatever T2 is pointing to. Now we have X and Y, where X, we know the midpoint of the median of X is less than the median of Y. If they're equal to each other, it's a different scenario altogether. But yeah, we can handle that. We can actually rewrite the code as well to actually handle when they're equal, so we can kind of do it all in one shot. I think all the different cases. But this is very useful kind of trick you can do for different kinds of, I guess it would be different data structures, like not just like you can use any kind of object here, and this is like a general, you can actually write like a general routine to do this, what do you call that? But you kind of would want to inline it though, because you want to get these const references. So it's not really, it's something I guess you'd memorize and kind of type it in each time. Something that's maybe it would be like this might actually be a good candidate for a this would be a good candidate for a what's that called, a macro. This would be a good candidate for a macro. So you could have write a macro for elements, like swapping to the smaller of a particular element based off of a particular condition. Presumably that condition is based off of that object, right? So you could swap, always get the quote unquote smaller object. I like that. I think that's good. I think it's good to do it this way. All right. So anyway, so yeah, that's a little bit better. So okay, so now we want to say so we want to remove elements, smaller elements that are too small. Remove elements are too large, right? Elements that are too small, we could say the total larger, we could say int. So the elements to the right are the elements to the left of our midpoint. The left of our median, we're going to say those need to be, those are going to be so we'll just say total or count. We're going to say count plus equals, so it's actually going to be 1 including the med A plus the difference between, it's going to be, it's not just the right, so there's also, we could say far right and far left. Far right and far left. Far right and far left, okay. And we say alpha far right or far left is a dot size minus 1, and alpha far right is 0. Yeah, and actually we could just set these to alpha left, alpha right, and same thing for beta. Maybe these should be constructors. Yeah, it's better as constructor. A little bit less typing to do it this way. Okay. And now we can say alpha dot left is left, or just this dot left is left. This right is right. And then same thing, this far left is left, and this far right is right. Okay. In this scenario, this situation, here we have the now like that's a lot less duplicated code, right? Like now all this updating happens, and the reason why with the far right and the far left is that way we want to associate that with the given range value rather than a particular vector and its size, because that's not going to change. And then so we can actually compute how many are to the right, right? So elements that are too small have too many values that are larger. So we could say count or larger count. We could say larger count. Start off at 0, or start off at 1 rather, and really it would be 0, and then we can say the larger count is going to be 1 plus the x dot far right minus, so these are indices, minus the value, it's going to be x dot mid plus 1. So it's the value, yeah, the inclusive range. So actually, we already have the plus 1 there. That inclusive range. Those are all larger. And then also, you're going to add, it's going to be on the y side, the y dot far right minus y dot mid plus 1 as well. So you add all of those elements that are to the right, including the medians as well, right? On both sides, because we know that y is larger than x. So, and we're going to say if and actually I think it's guaranteed every time that if this larger count is, now that's kind of tricky. I think it would be, yeah, that's a good question. Like, is it always the case that this larger count to the right, like maybe we don't even need to do these calculations. Like maybe it's just always true, and we could eliminate. Now, I guess one question here is like we don't want to eliminate these one by one. We want to eliminate them like a whole chunk at a time. So, I want to say all of the smaller values would need to be like Like I think it doesn't work if we have to calculate this. Like I think you can count this, but I think every time it's always going to be the case that everything to the left is too small. I think it just has to be every time. Is that true? Is it always just too small? It has to be, right? It has to be. Otherwise, yeah, because if the value you picked is the median, then then they're all too small, right? Basically, what we're saying is that none of those could be the median. One of them could be, maybe. The particular order statistic you're looking for. See, that's a good question. Like, how do we know that we can eliminate all of those in one shot? How do we know that? Do I know that? Huh. I don't actually know. That's a little confusing. That's maybe a kind of a hole in our algorithm, sort of, because we're trying to get any arbitrary order statistic in logarithmic time, not just the median. The median has special properties. Actually, all the elements that are too small, there's actually an index that we can take. Yeah. So, okay, we can calculate this in constant time still, but it's not necessarily everything that's smaller than this order statistic. What we need to do is say everything to the left for which after that point the number of things to the right are, we have too many, we exceed the total larger. Everything to the left of that we eliminate. And actually there's a function we can calculate. It's a linear function. It's a one-to-one function where the elements from the larger array are all counted immediately. However, the elements from the smaller array, the ones that are larger, are counted as well. And so I guess the index itself, like, because we could actually eliminate the median itself too, by the way. So we can include even the median. We would take all the elements that are larger than the median, and that's also kind of a constant. And then we'd say, okay, there's some difference between the number of things that we've counted so far and the total that's permissible. So we add, yeah, so we would have some difference. Now, if that's a positive number, that means that we can include some of these smaller elements, including the median. And that's how many we can include. So we would start, I guess the index we'd start at is the median index. And if we can include one more element, which would be the median, then we would shift. So actually, well, we would start to the right. We'd start one index, we'd start the median plus one. And we would say, if we can include one, then we could shift to the median. And what we're going to do is we're going to update our left bound to that particular index, right? So if we could include one more, we would actually shift to the median. If we can include 0 more, then we're done. If we include 3 more, then we would shift from the median and include 3 elements to the left. Yeah, it's a little confusing, but that actually there's a function to do that. We don't have to do that iteratively. Like we don't have to do, add, sort of move one by one. We can actually calculate what index that is. So if we could do like 3 more elements, then we can move that index to include 3 of those smaller elements. So we would subtract 3, and that's where we would set up our new really it would be our new left bound, right? Yes, so that's kind of nifty, kind of interesting. So we can do that in constant time, and that eliminates some, so that allows us to handle arbitrary sized order statistics rather than only the median. And I think you would still do the same thing for the median, but it's a little more precise, I guess, to do it this way. So yeah, so let's, where are we? Hour and a half. Okay, that's a lot of time. That's fine. So all right, so we're not going to count the smaller median value. We have our larger count. We're going to say our difference is going to be the larger count. So it's the total number. So the total larger minus the larger count gives us how many elements that we can include. And we're going to say new left is going to be the x dot mid minus this difference. So it's x dot mid plus 1 minus this difference. So we're going to move our new left. We're going to say we're going to move it to the right of the mid. So we're not going to include the midpoint, the median. And we're going to say, okay, we're going to count all these elements to the right of x as well as all the elements to the right on y. All of those included, except not the median is included in the bottom one. The median is also included, not included in the top one. Those are not going to, we're not going to change that. That's the larger count. And then we're going to take the total number of larger that we're supposed to have, take the difference between that larger count, and say, okay, this is how many elements that we can have to the left. Right, that's how many smaller elements we can keep, potentially keeping the median of the top of the smaller one. The one I guess I'm kind of envisioning it as if it was on top. And that doesn't necessarily mean we get rid of everything to the left. It's just there's a few elements we can keep, but everything that we don't keep, we remove. So we update our new left, and we say x dot left goes to new left. And then remove elements that are too large is a very similar routine. We have a smaller count. I see why this is hard, because this is pretty involved. And it's going to be, so now it's on the other side. Now we're doing elements that are too large. Now we're going to count everything that's smaller. So this is far left. It's actually going to be the midpoint minus the far left plus 1 to be inclusive, right? These are indices. And then on the other side we say the mid, so y is larger. We say the mid minus y dot far left. We're not going to plus 1. We're not going to include the median as well. We're going to do a similar thing, kind of a mirrored thing. And then we're going to say our diff is going to be the total smaller minus the smaller count. And then now we say that our new right, so we're going to take all these larger elements that are too big and get rid of those. And we're going to say we want actually a new right is going to be, it's going to be actually not including the median, so it's x mid minus 1. And this time we're going to add the difference. So if we could include the median, again, we'll add it. And if we could include a few other elements too, we'll add those too. So we say x right goes to the new right. And it's actually y right that goes to the new right. And this is y mid rather than x mid. Yeah, this is definitely a very atypical kind of an algorithm, atypical problem. This probably has a very concise solution too, which is kind of ironic. Yeah, so remove the elements that are too small, remove elements that are too large, which is kind of, it's a sort of a mirrored thing that you do. Larger count, smaller count. Now Excuse me. So what can happen is we might get to a point where, excuse me, you want to check both of the median values to see if they fit the descriptions. That's one thing. So like where we actually stop looping, but this is kind of what we would do for some time. We keep eliminating elements left and right, and also if they're equal to each other, if these two are equal to each other, then you can set. I guess what you would do if they're equal to each other is you can kind of do the same thing, except you would. You could consider. You could basically write the same routine again, do the same routine again. I would say swap the two and perform the same routine again. And yeah. So in one case you assume one is smaller than the other, and in the other case you assume the other is smaller than the other. And you do, yeah, so you do it that way. So you would do, so let me show you that. So it would be kind of interesting, but so I want to make this a lambda expression. Auto remove ranges, or yeah, remove, or just modify ranges. And this will take, try to explain how to do this. Hard to explain, hard to explain. Const range x, const range y. Now actually, these aren't const. The references are const, but we are actually going to modify these. So range x, range y. These aren't const. It's actually incorrect. Remove elements that are too small, so we can do this x and y. And we would say modify ranges x, y. So what you'd want to do is actually remove this and move this here. And we would say if, so we have T1, T2, alpha, beta. If they're equal to each other, if they're equal, then we want to modify ranges of alpha, beta, and then swap the two. And then beta, alpha. Else, then we do this here. It's taking me quite a bit of time. Add another 15 minutes. Actually, we'll add another half an hour. That's fine. Okay. So now we would say, otherwise they're not equal to each other, the medians. So if they are equal, we can do alpha, beta, and then beta, alpha, right? Do the same, basically same two routines. One assuming one is larger than the other, and see how much, what to eliminate. And if we are otherwise, we can say range T1, T2, alpha's median is greater than the beta median. Then we'd swap T1, T2, and make sure we have the smaller of the two. And then range X, range Y, we can update and we could do it this way. Yeah, that actually works fine. Set X and Y, these references to the, now, these are just const pointers. Pointers to a const range. Actually, they shouldn't be. I don't know if this works. Does this compile? Let me just see something here. Wondering if it compiles. Start with that. Oh, total larger. Oh yeah. Forgot about that. Actually, this could go outside here too. Some of these. Yeah, I was gonna say I think this is incorrect. So we do want to modify these values. I don't think they could be const. Because when we modify these ranges, they are going to change these things. These are not const references. These are references. Okay, so it compiles and runs. That's interesting. All right, so now, right, move elements that are too small, move elements that are too large. If we are equal to each other, the two medians, then we can do both ranges considering one to be larger than the other, and then vice versa. But if not, then you can only consider one to be larger, and you have to perform things that way. Yeah, so now what we want to do next is, this is kind of what our code's supposed to do, kind of what we want. This also could be captured outside as well. This doesn't need to be inside. Total larger, total smaller. Actually, I don't really need a total. You just do total smaller, total larger. Don't need, yeah. Part of the issue here is how do we finish this? So we modify our ranges in this loop, and we do that over and over again, right? Compute the mid again and the median again, and then keep modifying these ranges. When do we stop? So we stop if either of these median elements are what we need, or if, so check that either median, either element, the target order statistic, element is the target order stat. If so, return it, turn that to the value. check also both ranges at least one value, and then return as well. Not, then throw an exception. Could do it that way. That's probably better. Really should be an exception that we throw. I think in Python it's called the except library rather than exception. We'll just do runtime error. Is it a runtime error? Yeah, we call it runtime error. That's fine. Whoops, didn't mean to click that. Okay, so if either element is the target order stat, so how do we check that? Well, the number of things that are smaller should be equal to the orders, the total and smaller. We could do it that way. So we can actually calculate this. So I kind of want to check that also while modifying the ranges. That's probably also something to do. Maybe we can throw that in here. Could return a tuple here maybe. That's a tricky thing about using lambdas. I guess what you would do is just check yeah. Let me see. How do we do this? It feels like we'd want to compute the larger count and the smaller count. We could write subroutines that do that, and then move them outside of the modify ranges, and we could do both of those subroutines. And so the modifying the ranges could be, yeah, you could do that. Just like count, like a counts routine that gives you a tuple, and then you could just also check for both of these, like check count, check the smaller count on both of these each time you call the modify ranges, and then you'd break here. You do something like that. I think that's okay. I think it's reasonable. The problem though is that you don't know which counts to retrieve without knowing which ranges to operate on, which is why it's kind of tricky, because you need the context to know which ranges to operate on. So you could do another kind of we could try that. So calculate count. So you can do this with the right order of on the ranges. Range X, range Y. And yeah, and then you don't actually need the total larger, total smaller. Just have these. Keep it simple. Larger count, smaller count. We'll use a tuple. We could try this and see how it goes. And okay, so calculate counts allows us to remove this code out, and we could just have int small count, int large count. Smaller count, larger count. Then we can just pass this into this routine. So now we can break this up, and so we have a larger count and a smaller count already, and a larger count and a smaller count provided. And now we can say calculate, or compute is probably better than calculate. Alpha beta, and we can say const auto ref, we just say like T1, T2. I don't know. I want to say like small, large, or SL, small, large, yeah. And then you want to do the same thing for beta alpha. Small, large again. I guess my question is, can you rewrite these? I don't know if that works. You have to declare them. So alpha, beta, beta, alpha. And the reason we want to do this is that we want to have access to these small, large values, and we could check to see if small is equal to total smaller at any point, then we can return. That's why I want to do it this way. I want to expose these to this outer sort of expose this to this loop, I guess. So outside this loop, we want to expose, like we want these routines to be executed in this fashion, but we also want to expose that part of the calculation. That's kind of why we want to return those values and then pass them on in between, because obviously these returning inside of these lambda expressions doesn't really help us as much as returning right here. Right, we want to return to this lambda expression. So what we'd want to do is then we have small, large, alpha, beta, small, large, alpha. Now, I don't know if this will compile. That's one of the things I want to check. Does this compile at all? What does this do? Undeclared identifier. Oh, I'm wrong. No, I'm very wrong. This total doesn't change, but I was wrong. I was wrong. Okay. Let's try again. Does not name a variable. I don't know, how do you need to declare new variables every time? Can you use structured binding CPP? Optional identifier list. Any number of attributes, CV auto, ref qualifier, identifier list comes introduced by. Oh, so this is a declaration. Oh, an alias to existing object like a reference structure button does not have to be reference type. Okay, so I have to use new variable names again. That's annoying. I want to bind to tuples, that's what it is, but I see. Binding to data members. That's interesting. Yeah. You have to bind. I mean, not bind. You have to declare something in order to do this. That's annoying. That's annoying. Can I use tie maybe? I could maybe use tie. Oh yeah, tie is super interesting. That's what I want to use. Oops, didn't mean to click that. We could use tie as well. Or try to use tie maybe. Maybe we'll just use tie. Okay. Yeah, that doesn't work because these aren't just variables. You could do this though. How about that? Does that work? Okay, nice. And then now we can say a similar thing here. Excuse me, so it's X and Y. And now we want to call small, large. Okay. Now we can say if small equals total small at any point, same thing over here. If small equals total small at any point, then that actually means the median for alpha, we're going to return alpha dot median. We can just return the value. We don't need to return the mid. That's what I want to do. So there is some duplicated code here. I'm not entirely sure how to avoid it. Not entirely sure how to avoid it. Okay, so let's return. This should actually, if we don't return, then we want to throw an exception. So throw runtime error, no median. Missing order stat. If we don't return within this, if we don't return within this loop, and then here we'll say if alpha dot left is greater than alpha dot right, and beta dot left is greater than beta dot right, throw runtime error No order stat found. Not found. These should never happen. Okay. So we can call order stat on AB. Let's try that. I think it's, oh, let's order stat, we'll say order stat of total divided by 2. Yeah, let's try that. See what happens when we do this. If it compiles and executes, total smaller, we did mean total smaller. There are like no comments here either, which is not great. Should have some comments. Int, oh. Oh yeah, I see. So this should be 0 then. These actually will return integers. In the order stat, this will convert this integer to a double. Order stat not found. No. No. Stat not found. No. I'm going to say no range left. Range is depleted or deleted. It says, I guess depleted. Range is depleted. Yeah. Oh, that's interesting. Whoa. Okay. Well, alpha left, alpha left, alpha right, alpha right, beta left, beta right. Kind of expect to end up debugging this. This is rather complicated, this approach. Okay. Alpha left, alpha right, beta left, beta right. So we update, then one execution or beta left become beta right gets a +1. Oh, how does that happen? So on 1.1.3, So what we want to see is alpha left, beta left, alpha right, beta right. Oh yeah, we should probably not have the dot here. What happened? What happened? Alpha left 0, 3, beta right 3, or beta right 0. So this is not what I was expecting at all. This is not at all what I was expecting. So we compute these counts. So let's see. So 1, 3, 2. We should get our median should be a 1 and 2. And actually 2, we should return 2 immediately. Now, I guess what I want to check is small and large. Oh, I guess you do both of these. Yeah, you say or if, yeah, so you'd say if, and then if large equals total larger of, I see the issue here. Yeah. This is a tricky thing, but this should actually just return immediately, I think. This is the other way around. If we swap the two, beta alpha, and then over here, should actually be small equals x medium, and this is y medium. Yeah, these actually should return very quickly. Oh no, what? Man, what's going on? What is happening? Okay. Test. Let's see. Test. Okay. Test 1 and test 2. Test 1 and see how frequently we call these two. Which of these get executed? So we do test 1 and test 2. Let's make this one 2. Let's see what happens. Also, I'm lagging so much, I don't know what's going on. So first we call test 2, and then we call test 1. Now what's interesting is this should immediately, on test 2, this should have actually finished right here. Like we should have actually been done. So what are the counts? Small, and then large, target small and target large. Total smaller. We're going to put this on a new line. And total larger. Because basically we don't enter here. It's kind of what we were expecting to enter there, but we didn't. So for test 2, we said, okay, the median 1 is less than 2. Right? That's fine. Compute these counts. The smaller we have should be 0. I think, oh, small is 1. That's interesting. How did that happen? We got small should not be including a couple of things here. So the total smaller should be 1. Small on 1 should actually be 0. That's incorrect there. And then the large at this point should be, so target large should be 1 also. And the larger is actually 1. So large should be 1, not 2, and small should be 0, not 1. So these should be these should both be smaller. That's the first thing. Also, this would have returned right here. This small is small, and the total smaller is 1. Target small is 1, and small is 1, so this should have returned. First thing. And second thing, these are actually wrong, these two numbers, these counts. So these counts should be, this shouldn't include, modify these ranges. The larger count, so the smaller count is X is the smaller one, right? And oh, I see. Is that right? The larger count is for the things on the right side. So actually, I did this wrong. That's really interesting. So they're sort of inverted. It's actually, these should be swapped. It's actually the things that are larger than the smaller value is what the larger count is, which is correct, is 2. And the things that are smaller of the larger value, which is 2, is 1, which is correct. So large should be 2 and small should be 1. So actually it's reversed though, these values. So it should be the small and large. It's going to be smaller and larger, which I think we do that correctly. Smaller, larger, yeah. Smaller and larger. It's actually not the total small, it's the total larger, believe it or not. Oh, no. The smaller should match the total larger. That is so confusing. That's what? It's the larger elements. Yeah, that's really confusing. This is the larger count is all of the things that are larger on the smaller number. Yeah, so you compare the smaller number to the larger count. Larger than small. It's yeah, so it would actually be smaller than large and larger than small. Is more like what you would write here. Yeah, small and large. Count of elements. Count the elements that are smaller than the larger median, and the elements are larger than the smaller median. If you could imagine. So small, it's the total should actually be total smaller. Smaller than the larger median, so total smaller, and then the elements are larger than the smaller median. Large is total larger. But smaller than the larger median, so it's actually beta med, and this is alpha med. Well, I'm still surprised that neither of these did what they're supposed to do. Similar thing here. Again, small, large target. So small is smaller, but it should actually be y and x, if you could believe that. If you could believe that, if you could imagine. So y is the larger of the two, and x is the smaller of the two. So yeah, it's confusing. But still not working properly. So target small equals small. So test 2. Target small is the smaller, and small is it. So small and total smaller, return y.mid. How is it? Should only be one test case, I think, right? Should be 2, 2, 2, 2, right? Also my butt. Ow, my butt. Oh, we get the correct answer. Okay, it works. Hey, okay, I was expecting. That's what I was expecting. Oh, man. I have issues with my bum. It's not good. It's painful. All right. So it works in this case. Okay. Hey, that's pretty good. Now we don't handle the even case correctly. We're not there yet. How about this? How about this case? What if we have duplicates? Still the odd case, but see, what if we have duplicates? Just got the right answer. We do. Okay. I think the issue is we just don't do it correctly for the even case. So it seems. But that really shouldn't be a problem yet. I mean, it's a problem, but not quite a problem yet because we. It's not quite a problem yet because we shouldn't have a runtime error. See, that's a good question. So, excuse me. So 0101 test 1. Okay, it's not test 2. It's the issue. It's test 1. So we can compute counts here, and then we have compute set counts there. So we have test 1. Let's see what happens. So we have 0, 1, 0, 1, test 1, small 1, large 3. Okay, that's fine. I suppose. Target small, target large. Small 1, large 3, target small, target large. This is all from test 1. 1, 2, 3 times this is called? Oh. I didn't realize I did that. Didn't mean to do that. Yeah. Okay. So 2 printouts, and then we go to alpha left 3, beta right 0, beta left 3, beta right 0. So we're looking for this order statistic here is, I mean, total over 2 should be 3, right? So we're looking for the third order statistic. Okay, or 0, 1, 2 it would be, right? 4 divided by 2 would give you 2. So for some reason we don't find the third order statistic, and why, I guess, is the question. So target small, target large, alpha left, alpha right. So we should, what's going to happen when you pick, we're going to start with, I think, the midpoints, which would be 2 and 2, or 0 in both, right? So I think we start off with 0 and 0 initially. Alpha left, alpha right, and these medians are just zeros. And we say we want to eliminate values to the left and values to the right. And that gets very confusing. If they're equal to each other. So let's print, like, after we modify these ranges, after the ranges are modified. Let's see what happens. I don't actually know if my algorithm works correctly in this case, by the way. Apparently it doesn't. Apparently it doesn't. I'm just another half hour here. I'm spending a lot of time on this. So we get our targets are small, large, right? And we say, so we have initial alpha left, beta right. We get our small target. We call alpha left, alpha right. So somehow we end up with our alpha left ends up at 3, where it started at 0, right? After the first modify, the first. So, you know, these are equal to each other. You have 2 and 2. You say, you take the small and large, which we said was 1 and 3, which I think is correct, right? There's, we're saying the 2 in the top of the first one, the 2 in the first one is the smaller, the 2 in the second one is the larger, and so there are 1 and 3. We said that the 2 in the larger, the 2 in the smaller has 3 to the right of it, and the 2 in the larger only has 1 to the left of it. Actually, the 2 in the larger has 2 to the left, not 3, and not 1. How do we compute these again? That's confusing. Oh, right. It's because the order statistic we're looking for. Yeah, that's interesting. That's it's actually a bit skewed because maybe I'm doing this wrong. Yeah. I did calculate this wrong. This doesn't work properly for different order statistics. So when the total larger and the total smaller, the larger count and the smaller count, see that's really kind of special. So the total larger and total smaller should actually be computed with respect to the far left, the far right. Yeah. So these are actually calculated correctly, I think, the smaller and the larger. That does tell you how many things are. So how come though we got small 1 and large 3? Small should be 0, I think. Small should be 2, not 1. Should be 2, and large is correct. Large is 3, but small should be 2. Yeah, I think small should be 2. Let me see. Why should small be 2? X mid. So y is assumed to be larger than x. A larger range, right to the right. The things, the whole larger median. And so we're looking at the smaller count is the number of things that are smaller than y. So it's going to be the total things in x plus, not the total things in x, but well, it should include x. Yeah, it should include x. So x mid minus x far left, which in our case is 0, 0. So this is 1. And then also, I think I see the problem. And this is an issue with duplicates, not just with even things. I see the issue. Because there could be things, because if we're dealing with duplicates, there could be things to the right of this median x that are less than or equal to y that won't get counted. That's very interesting. Wow, all right. So there aren't as many things in y that are, oh, I see. So we don't eliminate, we don't actually have the right number. So actually you would be done immediately, but we don't actually get, we can't eliminate quite as many things quite yet. I guess. Because I think we could still eliminate, like I think the algorithm will still work. Possibly, I gotta think about that, but it won't count some of the elements that actually are smaller. So it'll give you a, it won't eliminate things as easily. Which is why this diff moves us all the way to the left, is that actually this number of smaller count should be larger. And then so, because the smaller count is not larger, this diff is larger. And then we take this difference. And then we could say, well, we could just say this is going to be, so we just modify these to the maximums and minimums. So we would say, oh, that's interesting. I see the problem. I don't actually know where the, oh, hold on, I gotta call a bunch of people. Oh man, streaming's hard, dude. Streaming's hard. It's hard to like focus for hours on end because it's just there's so many things that need your attention, require attention in the algorithm. Okay, that's what I was looking for. It's fine, I'm not complaining, but it's challenging. You have to call some people. I have like 3 people to call right now. Like 3 people to call right now. Yeah. So this, we're not going to make this any. We're not if the diff. This could be too big or too small. Like this could push us in the wrong direction. So what happened is if our smaller count is really small, then our diff could be really big, and then we end up moving very far to the right or very far to the left. I want to say something like that. I don't know. I'm doing this wrong. I don't know. Something weird's going on here. Somehow I'm doing this wrong. So what's the diff? What's the new left? After all these calculations, we get small, large, target small, target large, alpha left, alpha right. Yeah, so our small and our large, we get this alpha left. Alpha left is affected by what? New left, which is affected by the larger count, which is 3. So large is 3. Total larger, excuse me, is total larger should be 1, right? Target large is 1. So this diff becomes -2, and we subtract. Yeah. So that's really interesting. We can have a total larger is actually smaller than the larger count. Whoa. That's kind of weird. So how does that, what happens there? So we would say, you could just say like, the larger of these two, where it's at least 1, the diff is at least 1. Yeah, because if the diff is negative or 0, well, the diff could be 0. Let's just say that this is always larger, at least non-negative. I think that's what I want to say, something like that. Same thing over here. Not expecting this to be negative. Not expecting this to be negative. I don't really know what happens though if we do this. I have no idea what's going to happen. Okay. Oh. 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 My body. My body. My body. My bum. My bum. It's aching. Okay. Alrighty. Just thinking it's 3 people to call, and I'm like, oh, it's a hard problem. What happened? Remove elements that are too small. We get this large. So the small and this large represent how many elements to the left, how many elements to the right for each median that we know are too big or too small. So for the smaller median elements, we know the number of things that are larger are the elements to the right that are larger, and sorry, for the number of elements that are smaller than the smallest median, that's I think what small represents. No. The small represents the number of elements that are definitely smaller than the larger median, and then the larger count represents the number of elements that are definitely larger than the smaller median, which we know in our case the larger count is 3, and then the smaller count should be 1, right? Because there's only the other median we know is smaller, right? Yeah, in this case, we're assuming 2 is less than 2, quote unquote. 2 is less than, or yeah, we'll assume 2 is less than 2 in the first case. So that's fine. But now I want to say, how do we update our medians appropriately? Well, what the idea is, if we know there's a certain, so for the smaller median, the elements to the left are, we want to eliminate those because there are a number of them that are larger. Now, as it turns out, there are no elements to the left to eliminate. Well, you could eliminate the median itself, right? That could happen. The left side could get bumped up to the left plus 1, which is what's going on here. Left side could get bumped up here, which it would. It's not the mid. Yeah, it is the mid. Yeah, it would get. These are things from the midpoint, not from the left side. So this should get bumped to 1, which it does. Yeah, that's actually fine. Yeah, that's if there are too many things you know that are larger. Now, the tricky thing here is that the total larger is 3, or the total larger that we're looking for is, I think it's 2. And so this is also really confusing. Before, the total larger, because we're looking for the third order statistic, total larger should be 1, and the larger count was 3. So we got 1 minus 2 is -2, and our diff was then adding 2 rather than -2. So we ended up, instead of at 1, we ended up at 3, which was way too far. We do end up removing our median here because it's, because it's nowhere near what we're looking for. Now we can remove more than that median, potentially, which is what happened if there are so many elements that are larger that there's no way. So actually, yeah, this actually was fine. This was actually fine. We completely eliminated this side. Now, this might be slightly incorrect though with this difference, because it should be this. We actually could just subtract the difference directly, right? So if we had a negative, yeah, see, that's a subtlety. Where this is going to point us, this will actually point us to I guess like the quote unquote well, actually I don't know if that's right. There's so many things that are larger that we can we can move this median. We would need to move this median over quite a bit to compensate for that. That's kind of what's going on here, and we can actually push it outside of the range altogether. So we would need to include, in order to have all of those, in order to get anywhere near the order statistic we're looking for, we would need to compensate by removing diff number of, or adding, shifting diff number of if it's a negative, if diff is a negative number, we actually have to shift our median to the right by that number of whatever that difference is from the median itself. So actually, I think it's actually, we don't have this +1 here. I think in both cases too, it's the same thing. You don't actually modify these things. I think this is correct, but then something else happens here. It's kind of strange as we go further down, as we progress. How are we doing on time? This is not a clean, concise solution. Did that twice? Why did I do that twice? So I don't know. I don't know if I'm solving this anytime soon. I have a whole bunch of people I have to call too. It's getting excessive here. So this alpha left, alpha right. Yeah. So alpha left just shoots right over, right off the edge. Right. So alpha left is gone. What happens now, because they were equal, we did the same thing on the other side as well. We did as if now what happens to beta left, beta right is now the question, right? Alpha left, alpha right, beta left, beta right. Now we modify these ranges again. Now this time, so we basically eliminated the top portion. Now we're going to see what do we eliminate on the bottom portion, right? And the bottom portion, we should actually have moved the median. We should have actually eliminated the right side. So we actually should have gone down to sort of the beta right should have gone down to 1. And let's see. So let's see what happens here. So now we compute counts beta alpha. This should actually give us the inverse of what we had before. So small and large is 1, 3. This should be, so that's interesting. This gave us 1, 3 again, which is weird. Target small, target large, alpha left, alpha right, beta left, beta right. Small and large is 1 and 3 again. So it should have given us something different. That's actually not correct, I think. What happens when we compute these counts on beta and alpha? Oh, well, the mid didn't really change. We just changed. We didn't update the mid yet. Yeah, we didn't actually. Yeah, okay, so we should be fine. We didn't. But why do we get the same values again? It's not. Well, I guess these ranges are the same. Basically, they're pretty much the same range. They have the same values right in mid. So it's, even though we've swapped the things now, you do actually get the same small and large, but now it's on beta and alpha. Oh yeah, it is swapped. Yeah, it is swapped. That's right. Notice that's right. That's right. That's correct. That's correct. Now the small is referring to beta and the large is referring to alpha. So beta alpha, this should be swapped to alpha beta. Oops, It's not. Beta alpha should be alpha beta. That might actually be why we're having runtime issues. I think it's actually fires here, these two, or maybe they don't. I don't know. Okay, so yeah, now that these two are swapped, now these two are swapped too. That's confusing. Okay, so now target small, target large is target small is 2, target large is 1, which I think is still the same. Now I don't know if these swap too. If the small and the large should now be pointing to different things as well. I think that's also kind of confusing. I think maybe that's supposed to happen too. Large and small get swapped with the total larger and the total smaller, because now you're in sort of different directions. That's confusing. I think that is actually the problem. That might be the issue. That's super confusing. That's insanely confusing. Because now you swapped beta and alpha. Now the small and the large are pointing to different things. Yeah, it kind of is like that. It kind of is supposed to be like that. Because you're gonna get the same small and large values. It's just now the small is representing beta and the large is representing alpha. But those also should be so it wouldn't mean anything to do the same check again. So you have to actually make the check on the total smaller now, as well as the total larger, which is super confusing, I think. Yeah, that's really confusing. Oh no. Oh man. And now it just happens to work correctly in this instance, but I don't know if that's right. That doesn't seem right. Something about that seems very odd. Even though you swapped alpha and beta now, you still get the same number for smaller and larger. That's really confusing. I gotta think about that for a minute. Oh boy, there's so many swaps going on here, so many things being exchanged and moved around. Oh, kind of losing the logic here. I think this is just an accident that it works out here. I think there's something very odd going on. So again, the smaller and larger values that we're computing, we're saying that the smaller and larger values that we're computing, we're saying that consider the first array to have a median that's smaller than the second array, even though they're equal. Suppose that that's the case, and now the smaller and the larger is the number of elements that are smaller than the element in the second array, the median in the second array that we know are smaller. Excuse me. And then similarly, the number of elements that we know are larger than the median in the first array. Now when you swap these two arrays, or not swap the arrays, but consider now, suppose that the element in the first array is now larger. Now it just so happens that these arrays are equal to each other, so you get the same result. in both cases. But what's different is we're trying to check. So no, maybe it is the same check twice. The thing that's weird is that we would just eliminate both ranges, I think. But actually oh no, I don't know. I think it doesn't make sense. None of it makes sense, man. None of it makes sense. I think this is supposed to be small and large. But then it breaks, right? Then it just breaks because then both arrays just end up emptying themselves, and that's it. But why? Hmm. Well, that's challenging. That is challenging. How do I deal with duplicates? I mean, the evens are fine. Like, well, we haven't gotten the even case yet, but that doesn't really matter. What really matters is the duplicates. Because we end up removing so many elements. Okay, so I think the logic just doesn't work correctly here, right? If we eliminate the first array, that makes sense because we have so many things that are larger, right? We have 1, 2, 3 things that are larger than that median, so we have to really move that median over. And actually, we can't. It won't be found in that array, right? But then the problem is that if we swap the order of the arrays, they're equal to each other, so we eliminate both arrays. That, I think, is not what we want to do. Yeah. I think what we would do then is pretty much what happens at that point is that we know that the element is not in the first array. And so we know the element's not in the first array. It can't be, right? You'd have to use the entire first array. So then I think what you can do is you could just add the whole first array and index into, yeah, so I have an idea. I think what you do is something like this. You handle, it's sort of an edge case. I'm going to add another 30 minutes. So there is an edge case here. Edge case for which first array is totally eliminated. If alpha left is greater than alpha right, then we're going to return the median is going to be beta of alpha and beta. Yeah, beta represents B, so we can return B of it's going to be a dot size minus 1, right? because these are indices that we're operating on. Plus, so we're going to say int x equals t, or just some temp, temp x minus a dot size minus 1. That's going to be b of t. Let's try that. I think that handles this case. Yeah, there you go. So x we said is 3. The size minus 1 is 1. X is not 3, x is 2. It's an index, but it represents the third. Subtract size minus 1, which is 1. Yeah, subtract 1, that index, and then you just have 2 minus 1 is 1. I think it's actually minus another 1. I think it's... That's so confusing. I think it's actually this. It's actually this. It's 2 minus 2. Yeah. X minus a dot size. Yeah. Right. So that's if you totally eliminate the first one and they're equal to each other, these two medians. All right, because then what that means is that you can't have. Basically, means that everything in the first array comes before the median that you're looking for. So you can just add. You actually already know what that. You would already know which order statistic you need in the second array at that point. All right, let's see. They shouldn't both be eliminated, but I think that's all we need. That handles that particular case. Let me just see something here. Let's just try again. We didn't really go over. So in the even case, also handle even case, handle even and odd cases. If total and 1 is 1, return ret equals just order stat of total divided by 2. Otherwise, ret is going to be order stat of, so it's actually going to be total minus 1 divided by 2. And then order stat of another order stat divided by 2. And we're going to say, or we could say just int x equals total minus 1 divided by 2. And then you just say x and x plus 1. And I think that's what you do in the even cases. All right, let's see if we can try a few different examples. Wow, it's taking me really a lot of time. Let's try, have those saved already. Let's try to use the example cases. I think, okay, I'm just going to say, what do we do if it's all empty? Gulp. Gulp. Alrighty. Which one is that? Which one is that? Oh no. It's one of these. How about this one? Yeah, I think these are the same. So we can just say, is it this? It's causing issues. Oops, whoa. How'd that happen? Yeah, we already had 1, 3, 2. It's got to be one of these causing problems. How about this? Wrong answer. Oh, okay. No kidding. Really? 1, 2, 3, 4. So we should get 2 and we should get 3. So alpha left, alpha right, and we can say just call 1, call 2, something like that. Lots of debug code here. All right, test 2, and we get, should be this one down here. Okay. Small, large, compute counts. Small is total smaller, then that's the right one is what we want. Large is total larger, the left one we want. Modify the ranges. It's called test 2, and then we actually return there. And we can actually print that too. Oops. So this gets called 4 times now. Wrong answer. So you get 3 called 3. We get 3 and 3. Huh, how do we get 3 twice? Total minus 1. Total is, these are definitely not the same things, but total is 4. 4 minus 1 is 3. 3 divided by 2 is 1. So x is 1 and x is 2. Yeah, that's correct. 0, 1, 0, 2. So first order statistic, or second and third order statistics. So actually this x plus 1 doesn't give us the right answer. So really this is the one we want to be interested in. So we have 0, 1, 0, 1, alpha 2, 1. That's right. We totally eliminate 1, 2. Oh, I see. We need to put that in bold. Oh, I see the problem. And then, oh no. Wait, yeah. Actually, the first one shouldn't give you 3. That's wrong. First one should give you 2. The second one's fine, I guess. I don't know why the second one gives us 3 exactly. The second one should actually end up in this case here as well, where if you modify these ranges, then what should happen, you should actually call both of these. Both of these should happen here. And it's not x left, it's going to be x. If x left is greater than x right, then you're going to take the other. Oh, that's kind of annoying. Depending on if you swapped or not. These ranges, which of these do these refer to? That's really annoying. Which of these array is this referred to? That's the one you want to index. I guess you need a pointer to like which. That's obnoxious. You need a const standard vector int pointer. A reference pointer. That's brother. Which. Oh boy. That's good. Yeah. Okay. Let me just say which array. Nice. That's always good. That's always good. It's not really an alias at that point. It's a pointer to. Yeah, that's just confusing. Yeah. Okay. So now we need to create these. This needs to be A, and this needs to be B. And then now you can say. Now you can do the same thing you did up there. You can do down here instead of so instead of B, it's going to be Y dot which array, which really should be just which array. Okay. Great. 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 And actually, you're going to dereference this array also, by the way. Yeah, so it's something that's more like this. Something like this. Oh no. This is pretty messy. Not ideal. These are addresses now. Oh! It's always good. Unqualified ID. So this is a pointer that we want to dereference and then take the address at that dereference pointer. Which is quite the thing. Operands to binary expression range. What is going on? Oh. This is no longer X, by the way. This is, oh, I see. X is up all the way up here. Oh boy. Just say index. Have enough code here to justify that now. Oh, wow. Requires pointer operand. Wait, what is going on? Total. Oh, this will be evaluated first. Oh. Gotta be careful doing that. Yeah. Gotta be careful doing that. Requires pointer operand. Wait. So, okay. So this is, what's interesting is, I think you need to use the What happens here? Oh. Okay, so this does, I think this does do what we want it to do. I don't know if you need this, by the way. It might. Yeah, okay, okay. It's kind of annoying. I'm interesting that we don't need to do this, or that this doesn't work. Kind of would expect this to work. No? Okay, anyway. So I have a pointer to an array that we associate with this range. Const pointer. Now, okay. So which part is returning 3? So actually the first part should be returning 2, not 3. The second part returning 3 is fine. It's actually this edge case I think happens. So let's go ahead and check this first part. We call it test 2, left 0, right 1, but yeah, val 1 called. That's kind of weird. This val. Oh, I see. Yeah. We print a bunch of other things before we print this value. Okay, that's kind of annoying, but that's all right. So it looks like we get through test 2. So how come? What do we get in this case? Alpha, beta. What do we get for a computation? Let's try that. So I have a lot of people to call, man. My friend is helping his mom, but I'm pretty sure he should be back now. I should give him a call, see what he's doing. It's been a while. I was gonna call him like a couple hours ago, but I got really hung up on this. I was not expecting this to be so difficult, to take so much time. In the first instance, alpha, small 1, large 1, target small, target large. So I think that's correct, but I think these are reversed. So the smaller, oh, that's interesting. So yeah, we end up with the smaller and the larger. But these are, the larger has 2 that are smaller, not 1. So we should have gotten 2, right? This 3 has, oh, I think I see the problem. Oh, that's really awkward. Oh, that's why. I see the issue. We know that there's 1 smaller than 3, but there's actually more than 1 smaller than 3. There's actually 2. There's some amount to the right that's smaller than 3. So we shouldn't terminate early, I think, on these. I think that's a tricky thing. Yeah, I think that's part of the problem. Yeah, I think we should terminate when our median range. I think when our ranges are down when they're equal to each other, then we can check this. So yeah, we should only do this when and we should do this for both sides, right? All these cases. So we would say we should only make this check when so on the right side is the beta or y left is equal to y right. Should only do this when we get to the end. And same thing, x left is equal to x right. Whoops. This is so confusing. I don't think this is going to be correct, by the way. I think I have to just stop and take a break because this is just like, it's too much. Yeah, I think you should only perform those checks when you're on you only have one element left. Otherwise you terminate too early. And I think also those checks, I think those checks could be wrong too when, I think those checks could always have the possibility of being wrong. Because well, let's just try the other possibilities first, the other test cases. I think we'll come up with issues. I have a ton of debug output too. Yeah, something happens that's wrong over here too. There's some null pointer thing that happens. Which one would that be? I think it's one of these. One of these gives you issues. Let's see. Is it this one? Seems to be this one. Called the first, yeah, right here, causes problems. I mean, if it's empty, then I think this is the issue, right? This mid, this just gives you an error. Calculating the medians. We'll just say edge cases. A.empty, and return actually you have a if b.size, it's odd, b of b.size divided by 2, else x equals b.size divided by -1 over 2, return b of x plus b of x plus 1 divided by 2.0. Something like this. So you'd say const vector reference x and y, and you'd say if a is empty, set x to b. Oh no, actually that's all. That's all. I just say if a is empty, we go to b. Otherwise, so it's either a or b is empty. Let me just say if A is empty and B is empty, and then if either of them are empty, so if they're both empty, then you just return 0, I think. I think they're not supposed to be empty, but I think both can be empty, I guess. Yeah, they could both be empty. No, well, one of them is not empty. M plus n has got to be at least 1. Okay, so they're not both empty. But if one of them is empty, then if it's A, it's empty, then you set this to B. If B is the empty one, you set this to A, and you use X. And Y would be the other one. Which is A and B. And so we'll say, so X is going to be the one that's not empty, and, oh, I did this wrong. No, did it wrong again. Yeah, it's X dot size, X dot size, into T, so X of T plus X of T plus 1. Something like that. This should handle these pesky cases that we're dealing with here. There we go. Okay, the ones that are crashing. So the ones that are not crashing, let's try some things. All right, they're correct. Let's just go through a bunch of random tests. Let's just take some random things. It's bound to be something that crashes here. I really need to go speak to my friend. There's folks I need to speak to. I don't know, we can add some random things here, just 70, maybe 100 times, a bunch of times. Maybe just add, 1, 2, 3, 4, 5, 6 here. 1, 2, 3, 4, 5, 6, 7, 8, 9 here. And then we'll add, I don't know, some random numbers. 20 and 5. Maybe 1 and 2, something like that. How about these? Some random test cases. Let's see what they do. Nice. I think I could just take a break. This ended up being way too complicated. This is like, it's not working. There's some idea of an algorithm, but it's too complicated, man. I don't know. It's not working. I'm gonna have to debug all this, figure out what's wrong with the algorithm. I think the basic idea makes sense, but it's definitely let's say, just very challenging. What's that? Yeah, this takes way too much time. Dude, this is a lot to code. It's not even right though, actually. That's the thing, so I'm not even correct. Not necessarily. I think my algorithm just doesn't make sense. So we underflow here, right? This alpha left goes underneath 0 somehow. How did that happen? What happened there? Yeah, we have to debug these things. I have to just debug it and find out what I did wrong and what I could do right to get this correct. Again, I think the idea is correct. It just doesn't seem to be implemented very well. There's probably some stuff I'm missing in terms of the idea. Yeah, we'll leave this where it is. All right, let me stop here just because I gotta give my friend a call and I don't know what happened with him, but he probably texted me. I was kind of expecting him to maybe call me. Yeah, so that didn't work out. That didn't work out. We'll make this a part 1. Let me change the title. So yeah, thank you for watching. Pretty rough. Pretty rough. I don't know what to say. It's hard. I guess it's a hard one. I thought it wasn't that hard. I thought this would be fine, but nope. Nope, no sir. Ended up being quite a bit more challenging than I was expecting. Ran into quite a few issues. Thank you for watching. I will talk to you soon. A friend of mine I'm going to go spend some time programming with. I missed a bunch of things. I was supposed to eat. I was supposed to call my friends. Supposed to call my mom. Call my sister. Like it's, what a mess. Why is programming so hard, man? Why is programming so hard? So hard. All right. Take care. Talk to you soon. Definitely gonna have to check out the discussion after I fix my solution. Check out the discussion to find a very concise way of doing this and see how far we were from the better answer. All right. Take care.